All right, so what we're going to try to do is we're going to try to show you a basic idea of a proof that a particular sequence converges. This is our particular sequence. So for something to actually converge, it needs to satisfy the definition that we have chosen for convergence. Right? Now this definition is, we've talked about this in class. And what we saw is that there are two things that we need to construct. We need to construct a real number a and a positive integer n based upon epsilon. Right? And we need that these things that we construct work for two arbitrary things, or mostly arbitrary things, right? Any positive epsilon, any positive number, and our n has to work for any positive integers larger than that, right? And it has to satisfy this condition, right? This is ultimately the condition that we are trying to satisfy. Okay. All right. So if we look at our sequence, if we just look at the values, right, -2, a half, right, we have a -1 to the n, so the 3 is going from, we're adding 3 or subtracting 3, right, our n is getting a -1, -2, etc., right, we have a 2n down here. And if we look at the terms of the sequence, the pattern doesn't really show itself for a while, but if we look at this is a MATLAB kind of extrapolation of the first 100 terms, and we see that this thing eventually seemed to settle down around -0.5, right? So let's, in the proof, claim that we have -0.5 as the thing that we're converging to. It sure looks like we're converging to that. Okay. All right. So the next thing we need to do is we need to construct an n from an arbitrary epsilon. So we need it to be less than any epsilon, so let's stick that epsilon over there. We're going to do things to try to figure out what our n is, right? And we need to be close, arbitrarily close to this -0.5, right? So the difference, right, this minus sign indicates difference, right? The minus sign along with the absolute values indicates the difference between this number and this number. Okay, we need that difference to be arbitrarily small. Okay, now doing a little algebra, we see that this thing happens to be equal to this, right? And if we still need it to be less than epsilon, the absolute value and the -1 to the n are going to kind of cancel out. The 3 and the 2n are all positive, so we're good to go there. Okay, so for this condition to work for this n for any epsilon, this ends up being the condition that we need. But since we're going to talk about what the value of n is based on epsilon, right, we flip this around, so we need n to be some integer larger than this, right? So that's the thing we're going to stick with in our proof, right? That's the claim we're going to make in our proof. Now we need to actually do the work, right? Now we need to construct the proof based upon our constructions so that everything works. All right. So going back to our definition, right? We have now we've figured out, due to scratch work, how to construct an a for every epsilon that works, right? No, we've constructed the a first, right? We've constructed the n based upon our epsilon, and in the proof we're going to need to show this last part so that everything works. All right. So here is the plan for the proof. All right. Basically, all this says is it takes our definition and says that we're going to show that there exists a real number a. We're going to claim it by fiat. We're not going to stick it in a tiny little car and drive it around, right? We're going to claim it, right? Then we're going to let epsilon be arbitrary, and then we're going to claim our n based upon that epsilon, and then we're going to look at all of the n's past it and show that they satisfy the inequality, right? So this is our plan. This is the first statement in our proof. This is what we will do. Okay? All right. So now let's start doing it. So the first step was we needed A. Right? We need to claim our A, right? So we've claimed the thing that we're converging to. All right? Now we're going to let epsilon be an arbitrary number. Okay? So since this thing needs to work for all of them, we have to let people choose anything they want. Okay. Right? Now, based upon that, their choice of epsilon, we are going to construct an n that works, right? N needs to be an integer, and in our case, we're claiming that this any n, integer n greater than this will work. Okay. Next step is we're going to let our n greater than n be arbitrary. And again, our n, these are integers. These are terms of a sequence. In future proofs, I might not say this. Okay. Now, for such an n, right? Well, this is the difference between that term in the sequence. Every one of these passed our big N, right? We do the same algebra steps that we did last time and get to a fairly simple form. Okay? Now we take this and we move it over here, right? So this happens to be equal to that since we showed it in the previous step. But if we replace the little n with the big N, right? But big N was smaller than little n. So we're replacing the thing in the bottom with something smaller and positive. So it makes the inequality larger. Okay. Next, since n was larger than this, if we replace n with something smaller, right, we're going to end up with something larger still. Okay. Now, we have this fraction on the bottom, which we move around, right? We flip it and multiply. This cancels with that, this cancels with that, leaving us with our epsilon. And what we've shown is that epsilon is equal to this stuff, but it's greater than this, which is equal to that, all right? Which is exactly the thing we needed to show. Therefore, our original sequence converges, and it converges to -1/2 in this case. Thank you.